Hello everyone. So in this lecture, I'm going to talk about the superposition of complex potentials. So this is actually a very interesting technique that uses the linearity property of stream functions and potential and in general complex potentials in order to derive the solutions, analytical solutions for a combination of different flow types that we learned so far. So to find the flow pattern and also its analytical solution that results from multiple flow types, we use the linearity property of the governing equations, which are actually Laplace's equations, right? Okay. So, in other words, we are going to use this superposition to superpose and adding the complex potentials due to their linearity. Because they are linear, we can add them together. Okay? So in this lecture, I'm going to show you two examples of that. So the first example is we want to see what if we have, so we talked about like flow in a sector, potential vortex at Z naught, and source flow and uniform flow. What if we have a combination of these? So the first one I want to investigate is source plus uniform flow. Okay. So let's say we have a source flow, which we know it's like this. And at the same time, we have a uniform flow. So let me show it here. So say this is our coordinate system. Okay. And also we have a uniform flow, say in this sense, it could be something like this. So we want to see what is going to be their superposition if we have both of them together. So we simply, because of the linearity, we have to add these together. So the complex potentials are linear, so we can add them together. The complex potential of this one is a source flow. We learned that it's m over 2 pi ln z. And then for a uniform flow, the complex potential is uz. Okay, these are things that we learned in previous lectures and we talked about them. So the complex potential of their superposition, like source plus uniform, is going to be the addition of these two, which is going to be uz plus m over 2 pi ln z. So it's just superposition. And now let's see what does this entail. So first I wanna derive their velocity. So the velocity, complex velocity, is df over dz, which is going to be the derivative of f with respect to z, which is going to be u plus m over 2 pi. The derivative of ln is going to be 1 over z, so it's going to be m over 2 pi z, which equals to u plus m over 2 pi. Instead of z, I can just write it as r e to the I theta, and then here I just bring it to the numerator, so it's going to be e to the minus I theta. So instead of z, I can write it like this, and then I can write this, I just multiply this u by e to the I theta and e to the minus I theta, so I'm going to get e to the I theta here, plus m over 2 pi r, so I factor e to the minus I theta from both sides, and I get this. And this equals to, for the e to the I theta is cosine theta plus I sine theta, so this equals to u cosine theta plus I u sine theta plus m over 2 pi r times e to the minus I theta. So from this, I can say what are the radial and tangential velocities. So ur is going to be the real part of this, the real of wz, which is u cosine theta, not actually wz, is the real part of this. Let me show it to you. Here, yeah. So the real part of this part is going to give me ur, and then the imaginary part is going to give me the tangential velocity. So ur is going to be u cosine theta plus m over 2 pi r from here, and then the imaginary part u theta is going to be u theta, which is u sine theta. Okay, so I have the velocities of this, and this is actually minus u sine theta because that was minus I u theta. And based on these, actually you can plot that. You can plot the superposition of these two together, and based on that, based on these velocities that we found. So let's do that here and see how they look like if we plot them together. So say we have a source at the center. So I just copy this here. Slightly smaller. And then I make it blue. So we have a source here, and then we also have a uniform flow. So for a uniform flow, if you have a uniform flow, we are going for this part, we are going to see that it's going to look like something like this. Let me decrease that. if we add uniform flow to this. Same thing for this part. Gonna see something like this. And then for this one, it's going to go a little bit to that direction, and then it's going to return because farther away we have this uniform flow, so it's going to be something like this. It's going to look like something like this. Same for this component if you wanna write it, plot it. So it's going to look like this. And this one is just going to go this way, right? Because it's in the direction of the uniform flow. And then we can have other components like here. Can have something like this. It's going this way. This is going to do this way too. So we'll have something like this. And then, so let me see if I can do something here. Let me just, I want to replot something. So we are going to have, if I wanna, plot it from here. And then let me plot the one in here. Let's see what happens here, because we have two opposing velocities, right? So here we have U, a uniform flow, and then this is going to go toward the source, so they have opposing directions. So what's going to happen is somewhere around here, the velocity is going to be 0, and we are going to see something like this. So it's going to go this way. This is going to go this way. And here, the velocity is going to be 0. So here we call this as stagnation point. because the velocity there is going to be 0, okay? So now I want to say, so this is x and this is y. I want to find the location of this stagnation point, and we can find it based on these derivations that we had. So we want to see what is this location, what is the distance. Okay, so let's start to find the stagnation point location, stagnation point's location. So in the stagnation point, we know that UR, all the velocities are 0, so UR equals to U theta equals to 0. So from this formula, we see that U theta becomes 0 at when sine theta becomes 0. So it occurs at theta equals to 0 or theta equals to pi. And UR, in order for that to become 0, is when, based on this formula, when R becomes minus m over 2 pi u cosine theta. Minus m over 2 pi cosine theta u. Right, let me just check. Yes, it's correct. And so in order for both of them to be true, so at theta equals to 0, this cosine theta is 1, so this is going to give me a negative r, which doesn't make sense. So the only possibility is when theta equals to pi, and then r is going to be m over 2 pi u. So this distance is going to be m over 2 pi u. If the source is stronger, this is going to occur farther than the source. If source is the m, which is going to kind of shows the source, the strength of the source. If the source is weaker, it's going to occur somewhere closer to the source, okay? So this makes sense. And same thing for U. If U is stronger, then this is going to again occur closer to the source. And if U is weaker, it's going to occur farther from the source. Okay, so this makes sense. So now let's look at another thing. I want to find the shape of body or a streamline in the flow. Like I want to find a formula for these streamlines that I draw. So let's see how they will look like. So shape of body or streamlines in the flow. So again, the complex potential is UZ plus M over 2 pi ln Z, and Z is a complex number x plus IY, which also equals to R EI theta. So let me just write this down. So I'm gonna write this as U. Instead of Z, I want to write R E I theta for both of them, m over 2 pi ln R e to the I theta. So now I want to kind of simplify this. So this is going to be, we know r e to the I theta is just cosine theta plus I sine theta. So I just write it down, cosine theta plus I sine theta. This one, I can just write this as ln, I can just expand it as ln r plus ln of e to the I theta. And this is going to give me ln of e to the I theta is just I theta. So this is just e, this is just I theta. Okay. So based on this, this is going to give me fz is u cosine theta plus m ln r over 2 pi plus I, the imaginary part of that, and I forgot r here, u r sine theta plus m theta over 2 pi. Okay, so psi is the imaginary part of f, right? So because f is phi plus I psi, I want to know the string functions here. So it's going to be ur sine theta plus m theta over 2 pi. So this is going to give us all these, all the shape of all these can be found through this formula. You simply can vary theta and r, and or equal this to a constant psi, and then find the shape of that based on those. Okay. So for example, I can find one of them. So the shape of the streamline that passes through the stagnation point. Simply, I want to know what is the shape of this. I want to find an analytical formula for that, okay? So, for that, we know that it happens where the location of that is where theta is pi. We got it here, right? Theta is pi, and r is m2 m over 2 pi u. So we just equal to find that psi that passes through that. We just put these numbers here. So I'm going to get ur sine, instead of theta, pi, plus m theta, instead of theta, I just put pi over 2 pi, right? And sine of pi is 0, so this is going to be 0. So I'm just going to get m over 2. These two are going to also cancel out. So m over 2 equals to ur sine theta plus m theta over 2 pi. And this is going to give me the shape of the body that passes through the stagnation point. right? So simply, for example, you can evaluate this at different thetas and r's, and this at different thetas is going to give you the r. For example, say you want to see what is going to be the value of this, the r at theta equals to pi. Or like you can say different thetas, right? So say at theta equals to pi half, which is going to be, say, let me just draw it here so you better understand. So we know here it's going to be m over 2 pi u, right? Let me just make sure, yes. And then here you want to see what was going to be the value here. So you can set theta to be pi half. So then the sign is going to be 1 there. So you have m over 2 equals to ur times 1 plus m pi half over 2 pi. So these two are going to cancel out. And so you are going to have r equals to m over, I think, 4, if I'm not, 4u, if I'm not wrong. Because pi's are going to cancel out. Yeah, so you can find it like this. And then for the other one, like m 3 pi half, you can find it similar to this, okay? So and at different positions you can find this. So for example, I think at theta equals to 0, this is going to give us the r should be infinity, because it's going to be, there is not defined for that, right? So this is how you can find, actually you can evaluate r, or you can put just r. It might not be for defined for all the r's, right? But for all thetas, it's except like theta equals to 0, you should be able to get the position of this. Let me see. Yes. Yeah. Yeah, so this gives us a general way. So you can just plot it here by just putting different thetas, and then this will give you the shape of the stagnation point, right? And then for other ones, you can do the same thing. But then you need to find this psi for them is going to be different. This constant is going to be different. So this is like when psi equals to m over 2. Right? This is when it kind of passes through that stagnation point. Okay, so this was kind of a general technique, and in the next session, I'm going to use it for another type of flow, which is known as doublets. Thank you very much.